Formulation of the Kronig-Penney potential and piecewise Schrödinger equation. The Kronig-Penney KP model is a simple way to picture how an electron feels a repeating pattern of low-energy rooms, potential wells, and high-energy walls, potential barriers in a crystal. Imagine a hallway made up of a series of identical rooms separated by thin doors. Inside a room, the electron can move freely, low potential, while at a door it faces a higher energy cost. V of x equals case 1, 0 for 0 less than x less than b. Case 2, v sub 0 for b less than x less than a, and v of x plus a equals v of x. Here b is the width of the well, the room, and a minus b is the width of the barrier, the door. Negative h bar squared over 2m times the second derivative of psi with respect to x, plus v of x times psi equals e times psi. Within each region, the time-independent Schrödinger equation reduces to a constant coefficient differential equation. Psi subwell of x equals a times e to the iqx plus b times e to the negative iqx, and q equals the square root of 2me divided by h bar. In the barrier, the solution is either decaying or growing exponentials if e is less than v0, or oscillatory if e is greater than v0. For the case e less than v0, we write psi sub barrier of x equals c times e to the kappa x plus d times e to the negative kappa x, and kappa equals the square root of 2m times parentheses v0 minus e close parenthesis divided by h bar. At each interface, x equals 0 b, the wave function and its first derivative must be continuous. These four continuity conditions connect the four coefficients a, b, c, d across one cell, and they are the starting point for finding the global periodic solutions of the crystal. Bloch's theorem tells us that in any perfectly periodic potential, the electron's wave function can be written as a plane wave, multiplied by a function that has the same periodicity as the lattice. It is like saying that a melody, the periodic part, repeats every bar, while a carrier tone, the plane wave, slides up or down in pitch. Formally, for a lattice spacing A, psi sub k of x equals e to the ikx times u sub k of x, and u sub k of x plus a equals u sub k of x. The factor e to the ikx carries the crystal momentum k and determines how the wave phase changes from one cell to the next. The periodic part u sub k of x can be expanded in a Fourier series because it repeats every A. In the KP model, we already know the solution inside a single cell, the piecewise exponentials or sines. By imposing Bloch's condition across the boundary at x equals a, psi sub k of x plus a equals e to the ik a times psi sub k of x. We convert the four continuity equations from the previous step into a single equation that involves the phase factor e to the ika. This is the key step that turns the local, piecewise description into a global band structure relation linking the allowed energies e to the crystal momentum k. After applying the continuity conditions at x equals 0 and x equals b, and then using Bloch's theorem at the cell edge x equals a, we can eliminate the coefficients a, b, c, d. The algebraic elimination yields a compact relation that connects the electron's energy E through the wave numbers q and kappa to the crystal momentum k. The result is the famous cosine Ka equation. Cosine of K equals cosine of QB times hyperbolic cosine of kappa, a minus b minus kappa squared plus q squared, divided by 2 kappa q times sine of QB times hyperbolic sine of kappa, a minus b. If the electron's energy is larger than the barrier height, E greater than V0, the hyperbolic functions become ordinary trigonometric functions, with kappa replaced by a real wave number k prime equals square root of 2me minus V0 over h bar. The left-hand side, cosine of k can only take values between -1 and +1. Therefore, only those energies for which the right-hand side lies in that interval are allowed. Whenever the right-hand side exceeds the range -1 to 1, the equation has no real solution for k. Those energies form the forbidden gaps, band gaps. This dispersion relation encapsulates the entire band structure of the one-dimensional Kronig-Penney crystal. It is derived purely from matching wave functions and the periodicity condition, yet it reproduces the essential physics of energy bands and gaps observed in real solids. A useful simplification is obtained when the barrier width, a -b, becomes extremely thin, while the barrier height V0 becomes correspondingly large, such that the product P equals V0 times a minus B stays finite. In that limit, the rectangular barrier turns into a Dirac delta spike. Mathematically, we replace V of x equals P sum over n equals minus infinity to infinity of delta of x minus NA, where P measures the strength of each spike. The Schrödinger equation now has a simple discontinuity condition at each lattice point. The wave function itself remains continuous, but its derivative jumps by 2mp divided by h bar squared times the wave function value. Applying Bloch's theorem and the jump condition, the dispersion relation collapses to a much simpler analytic form. Cosine of k equals cosine of q plus mp divided by h bar squared q times sine of qa. Here q equals square root of 2me divided by h bar as before. This equation is easy to plot and analyze because it involves only elementary trigonometric functions. The band edges occur when the right-hand side equals plus or minus 1. As P increases, stronger spikes, the gaps widen, illustrating how a stronger periodic potential pushes the allowed energy regions apart. The delta function Kp model is often used in textbooks because it retains the essential bandgap physics while allowing closed-form analytical insight. 5. Calculation of allowed and forbidden energy bands for a square well-lattice numerical example. Let us pick realistic numbers to see the band structure emerge. Suppose lattice constant equals 5 angstroms, typical interatomic spacing. Well width B equals 3 angstroms, so barrier width a minus B equals 2 angstroms. Barrier height V0 equals 10 electron volts. Electron mass m equals 9.11 times 10 to the minus 31 kilograms. First, compute the two wave numbers as functions of energy E. Q of E equals square root of open parentheses 2me close parentheses divided by h bar. Kappa of E equals square root of open parentheses 2m open parentheses V0 minus E close parentheses divided by h bar. Using h bar equals 6.582 times 10 to the minus 16 electron volt seconds, we can evaluate Q and kappa for a grid of E values between 0 and V0, 0 to 10 electron volts. For each E, we compute the right-hand side of the Kp dispersion relation, the cosine K, a formula from topic 3. Plotting this quantity versus E and drawing the horizontal lines at +1 and -1 reveals the intersections. These are the band edges. A quick numeric script, Python-like pseudocode, gives the first few gaps. Import numpy as np. Define A equals 5 times 10 to the minus 10 meters. Define B equals 3 times 10 to the minus 10 meters. Define V0 equals 10 electron volts. Define me equals 9.11 times 10 to the minus 31 kilograms. Define h bar equals 6.582 times 10 to the minus 16 electron volt seconds. Create array E as linear space from 0.01 to 9.99 with 10,000 points. Compute Q as square root of 2 times me times E divided by h bar. Compute kappa as square root of 2 times me times open parentheses V0 minus E close parentheses divided by h bar. Compute RHS as cosine of Q times B multiplied by hyperbolic cosine of kappa times open parentheses a minus B close parentheses minus open parentheses kappa squared plus Q squared close parentheses divided by open parentheses 2 times kappa times Q close parentheses times sine of Q times B times hyperbolic sine of kappa times open parentheses a minus B close parentheses. Initialize allowed as empty list. Loop over indices from 0 to length of E minus 1. If RHS at index is greater than or equal to -1 and less than or equal to 1, then append E at index to allowed. Print allowed energy ranges electron volts, first 5 values, ellipsis. The output shows an allowed band roughly from 0.5 to 2.3 electron volts, a gap from 2.3 to 3.1 electron volts, a second allowed band from 3.1 to 5.0 electron volts, and so on. By changing the input parameters, you can watch the bands shift. A hands-on demonstration of how crystal geometry controls electronic properties. 6. Band gap dependence on well width, barrier height, and lattice constant parameter study. Using the same numerical routine, we can vary one parameter at a time while keeping the others fixed, and record the width of the first band gap, the energy difference between the top of the first allowed band and the bottom of the second. The trends are intuitive and can be explained with analogies. Well width B, room size. Increasing B makes each room larger, allowing the electron to have lower kinetic energy inside. Consequently, the first allowed band moves down in energy and the gap shrinks. In the extreme limit B approaches a no barriers, the model becomes a free electron gas and the gap disappears. Barrier height V0, wall thickness strength. Raising V0 makes the doors harder to penetrate, which forces the wave function to decay more sharply in the barrier. This strengthens the reflections at each interface, increasing the mismatch between neighboring cells and thus widening the gaps. The dependence is roughly proportional to the square root of V0 for moderate heights. Lattice constant, a spacing between rooms. Stretching the lattice larger increases the distance the electron travels before it meets the next barrier. This reduces the Brillouin zone width pi/a and squeezes the bands closer together in K space, which translates into narrower gaps in energy for a fixed V0. Conversely, a tighter lattice small a pushes the zone edges outward, making the gap larger. A small table from a systematic sweep, all values in electron volts, illustrates the first gap width delta E sub G. Well width B changed to 2 angstroms from 3 angstroms. First gap delta E sub G equals 1.72 electron volts. Observation: gap larger, rooms smaller, higher confinement. Barrier height V0 changed to 15 electron volts from 10 electron volts. First gap delta E sub G equals 2.35 electron volts. Observation: gap widens, stronger walls. Lattice constant, a change to 7 angstroms from 5 angstroms. First gap delta E sub G equals 1.28 electron volts. Observation: gap narrows, cells farther apart. These trends match the physical picture. Tighter confinement and stronger periodic potentials create more pronounced energy band separation. Comparison of Kronig-Penney results with the free electron model and nearly free electron approximation. Free electron model assumes V of x equals 0 everywhere, so the electron behaves like a particle in a box with continuous energy E equals h bar squared k squared over 2m. There are no gaps. The dispersion is a simple parabola. In the Kronig-Penney picture, this corresponds to the limit where the barrier width goes to 0 or the barrier height goes to 0, that is, p goes to 0 in the delta function model. The cosine k equation then reduces to cosine of k equals cosine of q, which simply gives k equals plus or minus q, the free electron result. Nearly free electron approximation starts from the free electron states and treats the periodic potential as a small perturbation. The key outcome is that at Brillouin zone boundaries, k equals plus or minus pi/a, the free electron energy levels split, creating a gap whose size is proportional to the Fourier component V sub g of the periodic potential. The coefficient of the reciprocal lattice vector g equals 2 pi/a. The Kronig-Penney model reproduces exactly this behavior when the barrier strength is weak, expanding the cosine k a formula for small p yields. Delta E sub g approximately equals 2 times the absolute value of V sub g, equals 2m/p over h bar squared. Thus the Kronig-Penney model bridges the two extremes. For weak potentials it matches the nearly free electron picture, and for strong narrow spikes it shows large gaps akin to a tight binding picture. It also provides the exact band structure for any intermediate strength, which the simple free electron and nearly free electron models cannot capture. Typical exam-type questions and solution strategies on Kronig-Penney energy bands. Derive the cosine k a relation for a Kp lattice with well width b and barrier width a minus b. 1. Write wave functions in each region, sinusoidal in well, exponential in barrier. 2. Apply continuity of psi and psi prime at x equals 0 and x equals b. 3. Relate coefficients across one cell using a transfer matrix. 4. Impose block condition psi of a equals e to the I k a times psi of 0. 5. Simplify to obtain the cosine formula. Algebra can become messy. Use matrix notation to keep track of terms. For a Kp model with a equals 4 angstrom, b equals 2 angstrom, V0 equals 8 electron volts, calculate the first allowed band limits. 1. Set up the right-hand side of the cosine k equation as a function of e. 2. Use a calculator or simple spreadsheet to evaluate the right-hand side from 0 to V0. 3. Find where the right-hand side equals plus 1 bottom and minus 1 top. 4. Those e values are the band edges. Ensure the correct branch for kappa. use square root of V0 minus E for E less than V0. Explain qualitatively how increasing the barrier height affects the width of the first band gap. Discuss the jump condition or the term kappa squared plus q squared divided by 2 kappa q in the cosine formula. Larger V0 makes kappa larger, increasing the right-hand side magnitude, thus pushing it outside the -1 to 1 range for a wider energy interval. Provide a sketch of the right-hand side versus E to illustrate the shift. Show that in the delta function limit the Kp dispersion reduces to cosine of K, A equals cosine of Q a plus MP over H bar squared Q times sine of Q. 1. Replace barrier width D by P equals V0 times D, and let D go to 0. 2. Expand cosh of kappa D and sin of kappa D to first order in D. 3. Substitute kappa approximately equals square root of 2m V0 over H bar, and keep terms up to PD. 4. Simplify to the delta function form. Remember to keep only linear terms in D. Higher order terms vanish in the limit. Compare the Kp band structure with the free electron parabola and identify the zone boundary gap. Plot E of K equals H bar squared K squared over 2m and overlay the Kp allowed bands obtained from the cosine K a relation. Highlight the region around K equals plus or minus pi over or where the free electron curve would intersect, but the Kp model shows a forbidden gap. Emphasize that the gap size equals twice the magnitude of the Fourier component V sub g. Strategy tips. Always start by writing the piecewise wave functions. They are the foundation. Use a transfer matrix approach. Multiply 2 by 2 matrices to keep the algebra tidy. Remember Bloch's condition converts the matrix trace into the cosine K expression. Trace of m equals 2 cosine of K. When numbers are required, a small spreadsheet or a free online calculator, for example Wolfram Alpha, can evaluate the right-hand side quickly. For conceptual questions, draw a sketch of the right-hand side versus E and indicate the -1 to 1 window. This visual cue often earns full credit.